This is the video of Chapter 5 of the book Elements of Financial Risk Management by Christoffersen. In this chapter, we will learn how to compute volatility using high-frequency data. The goal of this chapter is to harness the information of intraday prices to compute daily volatility. We will learn the 4 stylized facts of realized volatility and how to use realized volatility to forecast daily volatility in general. There are 4 stylized facts for realized variance. Realized variance is the one computed with high frequency data. The first one is that realized variance is a better estimator of daily variance than square returns. So from now on, if you have it available, use realized daily variance instead of the square returns for daily variance. The second stylized fact is that the autocorrelation function is very positive for about 50 lags. So that is the autocorrelation function for realized variance. Below is the one for square returns that it's also positive, but it doesn't look as nice as the one for the realized variance. The third stylized fact is that the logarithm of realized variance looks like the normal distribution. So in general, we're going to say that this is normally distributed with a certain mean and a certain variance. Finally, the fourth stylized fact is that daily returns standardized by the square root of realized variance are normally distributed. This is an example of Alcoa, that's a company in the US, where you can see that the empirical distribution looks very much like the normal distribution once it's standardized by realized volatility. Since we have daily realized variance from high frequency returns, we need models to forecast future realized variance. We are going to cover 3 models. The first one is ARMA, the second one is the Heterogeneous Autoregression model, and the third one is how to add realized variance to the GARCH models. Since realized variance has high autocorrelation for small lags, we can use an AR1 process to forecast future realized variance. However, one of the problems is that we observe realized variance with some measurement error. So instead of using AR1, we're going to use an ARMA 1.1 process where we add an error term. We use the log of RV for day t+1 so that we get a normal, and we use the normal distribution property of the log of realized variance. This is going to help with the assumption that the errors are normally distributed. Finally, we're going to forecast with an ARMA 1.1 process this way. So this is the realized variance on t+1 conditional information up to date t, and we are going to take the expectation of the ARMA 1.1 model and use the exponential function to remove the log. Hence, future realized variance is going to depend on phi 0, phi 1, theta 1, and the variance of the error. The most widely used model to forecast future realized variance is the heterogeneous autoregression. We're going to call it the HAR model. The 3 explanatory variables in this model are the daily realized variance, the weekly, which is the average of the 5 last realized variances, and the monthly, which is the last 21 realized variances. This model uses a linear regression, or OLS, to estimate the parameters. The main idea is to explain tomorrow's realized variance, that means the one at t+1, with the 3 explanatory variables. We can use the logarithm of all realized variances so that the error is normally distributed by construction. The forecast of RV depends on 5 parameters. Those are phi 0, phi daily, phi weekly, phi monthly, and the error variance. This model can be used to forecast not only tomorrow's volatility, so in this case it's RV at t+1, but also realized volatility over longer periods, say k days. So here we have realized variance that is from t+1 up to t+k, which can be used on the left hand side of this regression. Finally, we can incorporate the leverage effect into the HAR model by including today's return in the linear regression. The GARCH model can also be used to forecast future volatility. The GARCH-X model adds realized volatility to the GARCH 1.1 model. The realized GARCH model adds an error term to the modeling of realized volatility, and it is estimated via maximum likelihood estimation, assuming that the error term and the return standardized are jointly normally distributed. To compute the value at risk and the expected shortfall, we use the stylized fact that return standardized by square root of realized variance is normally distributed. Hence, the VAR is equal to minus the square root of realized variance multiplied by the cumulative inverse normal. And the expected shortfall also uses the normal distribution with the forecasted realized variance. Now we see how to compute realized variance with intraday returns. The first estimator is called the All RV Estimator. All because it's going to use all the data available. The main problem when using all returns is the bid-ask bounce. Now what is the bid-ask bounce? The prices are recorded during the day either at the bid or ask prices. You can imagine that there's a fundamental price, so here is the black line, and the red line are the prices that we observe during the day. Again, bid or ask prices. Therefore, many of the returns are bigger than what they should be, and many of the returns are basically jumps from bid to ask and back to bid. For this reason, the All RV Estimator variance overestimates volatility because of this big jumps between bid and ask prices. Later on, we're going to see how to correct for this problem. The second estimator is the Sparse RV Estimator. To avoid the bid-ask bounce, we are going to use returns over a longer time span, say 5 minutes, 10 minutes, or 30 minutes. The Sparse RV Estimator is also going to be the sum of returns squared, but in this case we're going to have, say, 5-minute returns. The only question is, what is the ideal frequency to compute the Sparse RV Estimator? Or what is how to choose the parameter S? To answer this question, we're going to use signature plots. Signature plots has the frequency of return on the x-axis. So here we go from basically 0 minutes, let's say 1 second, up to 20 minutes. And we have on the y-axis the Sparse RV Estimator. Notice that the All RV Estimator, which would be the one about here, overestimates volatility. As we increase the frequency, so here we increase to 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and so on, we see that the RV reaches a unique value. So at about 5 minutes, we see that the line becomes straight. Hence, the most widely used frequency to estimate a realized volatility is 5 minutes. The next estimator we're going to see is the Average RV Estimator. That is like computing 5 sparse RV estimators and then taking the average. What is the logic? We're going to compute 5 estimators at the 5-minute frequency. For example, we could use any other frequency. And then we're going to use a 1-minute grid, but we have to compute this 5 different RV estimates, each based on the 5-minute returns. How are we going to do that? So you can imagine that the first RV estimator is going to take the returns that start at 9:30. So those returns are going to go 9:30, 35, 40, 45, and so on. The second estimator is going to start at 9:31, and the return is going to go from 9:31 to 9:36, 41, 46, 51, and so on. And then the last of the 5 estimators is going to start at 9:34, and it's going to go until 9:39 to record the first return, and then 9:44, 9:49, and so on. Then at the end, we're going to have those 5 sparse RV estimators. Then the average estimator is just going to be the average of those 5 RV estimators. The next estimator is the RV estimator with the Autocovariance Adjustments. This is going to remove the bid-ask bounce problem. We assume that the lock price is the fundamental price plus some kind of error. This error is capturing the bid-ask problem. When computing the observed return, the two error terms arise. These error terms appear in the All RV Estimator 1 and 2. Since we're trying to correct for the bid-ask bounce, those 2 error terms should be negative, indicating that you go from bid to ask and then back from ask to bid. The fact that they are negative corrects for the overestimation of the All RV Estimator in its new estimator with autocovariance adjustments. Notice that these 2 terms are identical. Finally, to evaluate our forecasted variance, we run a linear regression between the true volatility, that in this case is going to be computed with a realized variance measure, in specific the average realized variance, and the forecasted volatility. This forecasted volatility comes either from a GARCH model, an ARMA model, or a HAR model. The null hypothesis is that B0 is equal to 0 and B1 is equal to 1 to have a good forecasting model. In conclusion, in this chapter we learned how to handle big amounts of data at high frequency to compute variance. The realized variance measure is the latest methodology to estimate variance. And finally, realized variance is very good to standardize returns to forecast future variance and can be used in GARCH models. This concludes chapter 5. Thank you very much for watching.